Welcome to Kinematics. Let's get started. So, there are several kinematic equations that consist of a constant velocity. Now, the first kinematic equation should not be surprising because, as you have learned in the previous lecture, that acceleration, the average acceleration, is equal to the change in velocity over the change in time. Change in velocity is final velocity minus initial velocity. Now, if you're wondering what this S, so T, change in T, this looks very similar to the problem below. Now, if you're wondering what this S stands for, all this is saying is the direction. The S is, you could put Y here, you could put X, Y, you could put Z. It's just saying the final velocity in some direction is equal to the initial velocity of that same direction plus the acceleration in that direction times the change in time. So if we rearrange this equation, it shouldn't be too surprising. We get this formula. Now we tend to shorten our delta t to t because usually our initial time we set to be equal to 0. Once again, you can use I or 0 to represent initial. And so that is a common symbol for either initial or final. And as we go through this presentation, you might find that some of these might have sub S's or sub X's or sub Y's or sub Z's. They're just different ways of presenting the ways of presenting a direction. Now, if we have a constant acceleration, if we take the integral of that acceleration over time, we will get our velocity. Shouldn't be too surprising. The integral of acceleration over time is the integral of dv dt time, and so you get that change in velocity. But your velocity is dependent on the position. So you have dv dt, but that v is just your dx dt or dr dt or ds dt, depending on what symbol you want to use. And so acceleration is not only but the second derivative of position. So if we want to integrate, we will get a relationship of the position with respect to time and acceleration, but also in respect to velocity. And so from doing those steps, we actually come to the conclusion of this relationship of position is related to your initial velocity times time plus 1/2 the acceleration times time squared. And so this is our second equation for kinematics under constant acceleration. Now we can take the former equation, the first equation and the second equation from the kinematic equations, we can plug them into one another, and we can derive this relationship. And this relationship is very handy, especially if you don't have time. So if you don't know time, this relationship is handy. So we will use these equations to be applied to certain variety of problems. Now in our problem sessions, we will go through this problem that's over here, but you can go through these steps and go ahead and try to figure out what do we know and what information can we get from there. So one form of acceleration that is very prominent in our life is the acceleration of free fall. This is the acceleration due to gravity. The Earth is constantly pulling on us, and we experience a force by being near the Earth. Now later on we will discuss how we can calculate this force field that we experience due to the pull of the Earth. But right now, we tend to just simplify it down and say that the acceleration that an object being dropped in free fall will experience an acceleration of 9.8 meters per second squared, and it will be always pointing downwards. It doesn't matter what you are dropping, the acceleration due to gravity is always going to be 9.8 meters per second squared, assuming you're at the same distance away from the planet. From the surface, if you're standing on the surface of the planet. Now this 9.8 is actually averaged across the Earth because when it turns out when you're on top of a mountain, the acceleration due to gravity is slightly lower. And there are places on the Earth that are kind of below sea level, and those are, of course, greater than the acceleration due to gravity. You will discover that there is actually a relationship to the distance from the planet to get this value, but we are not doing that right now. We're just going to leave it as a constant 9.8 meters per second squared. So we commonly use this acceleration of freefall. We use a symbol g. Now g only represents 9.8 meters per second squared. The negative comes in the direction. This is by choice. I always like to make my negative y direction point downwards, and my positive y point upwards. I tend to like to use a basic plane of x, positive x pointing to the right and positive y pointing up. That's the normal coordinate system that I like to work with. Now you may find online that some people will make downwards direction be a positive direction, and so they may use a positive 9.8, but that is because they are making their positive y direction point downwards. But I like down to be my negative y. So because of that, my acceleration in my y direction is going to be negative this g value. G is not negative 9.8. G is just the number 9.8 that we use to just fill in that blank so we don't constantly write 9.8, 9.8. It makes things in a nice symbolic format for us. So if you have a ball and it's tossed straight up in the air, at its very highest point, the ball's instantaneous acceleration is going to be what? Is it going to be positive, negative, or zero? You can pause to think about it. If you chose negative, you are correct. As I stated, I make my positive y-axis be pointing upwards. Therefore, the acceleration due to gravity is always going to be negative in my problems. In our problem sessions, we will go and explore a problem that's one-dimensional in the y direction, and this will deal with a person throwing a ball upwards into the air with an initial velocity. You can go through and try this problem on your own before you come to class, but we will work through it and show some assumptions you have to make. Now, one interesting thing is when you have an object sitting on an inclined plane, the object accelerates down an inclined plane, assuming it's frictionless and there's nothing else going on. Because it's moving from a zero from rest, it's of course going to accelerate if it's moving. Now, the acceleration due to gravity is always pointing downwards, but the object is not accelerating downwards, but along the inclined plane. And because of that, you're only going to see a part of it, and you're only going to see the parallel, what we call the parallel component of that free fall. So the force due to gravity is going to contribute to this motion of this block sliding down, but only in the parallel component. And because of triangles, you can look at your trigonometry and geometry, and you can see that the angle of the incline is the same angle as right here. I also tend to like to draw this diagram where I have my perpendicular component actually pointing in here, and then my parallel component pointing here. And so therefore it might be easier to see that this angle is also located right in between here. Either way, whichever diagram you like, it shows that the parallel component is related to the sine of that theta. Now, when we start working in two-dimensional space, there are some things that you have to take in consideration. One, this object is moving in the y direction, so it is experiencing an acceleration in the y direction. But it's also moving in the x direction, and especially in the case of projectile motion, our acceleration in the x direction is 0. So it's very common that our acceleration is going to be 0 I hat minus 9.8 j hat, meters per second squared. Now, if we had some external force happening in the x direction, that would change our acceleration in the x direction. But for most of these problems, until you get into physics 2, we will usually assume that our acceleration is 0 unless stated in the problem for the x direction. For the y direction, it is assumed that it's going to be negative 9.8, but of course there is always future problems where you could be on a different planet where the acceleration due to gravity is not negative 9.8, but something else. When we're dealing with these problems, it is very important to know what's happening in the x direction and what is happening in the y direction. Please take care in making sure that you break your problem apart in what's going on the x and what's going on the y. Sometimes I will do this by making a table and say this is what's happening in my x direction and this is what's happening in my y direction. And I will list everything I know about the position in the x, the position in the y, the velocity in the x, the velocity in the y, the acceleration in the x, and the acceleration in the y. The one thing that is consistent between these two components, the x and y components, that bridges the gap between x and y is time. Think about it this way. If you're throwing a ball up into the air, it's traveling both an x distance and a y distance in that time frame. That ball can't travel the x distance and the y distance separately at a different amount of time. That doesn't make any sense. And so, therefore, the time element is our key to both the x and y direction, and it's our link to being able to solve these type of problems. So you can find your velocities, you can find your time, your accelerations by these relationships. Once again, there's also, we need to break our velocity into our x and y components. Now, doesn't have to be a cosine or a cosine theta for x and a sine theta for y. You do need to look at your picture. But in this picture, because of where my angle is located, we will have a cosine component will be x, and our y component will be sine. In order to figure out a particle's speed at a moment, you need to take, of course, the Pythagorean theorem to figure out the magnitude of that velocity. And once again, you can also figure out the angle by taking the ratio of the y and the x components and taking the inverse tan. Now, acceleration points in the same direction as the change in velocity. There are several ways that you can change the velocity. You can change the velocity by changing the magnitude of that velocity, indicating a change in speed. But there's also another way in which you can actually change the velocity, and that's by direction. When you're going around in a circle, you can maintain and keep a constant speed, but you will have a changing velocity because the direction is changing throughout. In this situation, we do have an acceleration, and what you'll discover is that that acceleration is going to point inwards. This leads us into circular motion, which we will address in a couple weeks. In the end, we have a set of equations. We have our constant acceleration equation. Both of these equations are constant accelerations, and there's accelerations in the x direction and the y direction. There is one equation that's missing from this, and that's that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in distance. Okay? And so whether you want to use x or s or y, that is up to you. Now, it is important to know that these y equations we tend to change around, and we tend to make this y final equals y initial plus the initial velocity of y times the change in time. And since we know what the acceleration in the y direction is in this case, we can then just say subtract 1/2 g change in time squared. It is very common to see this type of equation over the former. But you can also apply this even in the z direction. These equations are all similar. I like to just keep it simple and just memorize these equations here, because the fact of the matter is you know the acceleration in the y direction, so you could just go ahead and plug it in for any scenario. You also know the acceleration in the x direction, and in most of the cases of dealing with projectile motion, our acceleration in the x direction tends to be 0. Now, of course, when you get into a more advanced level of physics, you'll discover that you don't necessarily have acceleration being 0 in the x direction, but that's going to come next semester. So in the end, there's actually several equations. Now, these are all the key equations due to accelerated motion. This one is just derived by the actual definition of acceleration, equation 2. Equation 4 and 5 are the most useful, although I don't know if I agree. I don't like how that's written. Equation 3 and equation 4 are the most useful. Now I stole this from another presentation, and so they, as you can see here, they use D. Also, the reason why I don't like equation 5 is that they use A sub gravity, and I didn't like that, because it shows a negative sign and it's flipping back and forth. But we don't need to worry about that. Okay, so we'll just cross that out. Usually they would use G as that symbol. Now there is one more equation that we deal with kinematics. That is only under constant velocity. If you use this equation, you cannot use the acceleration equations. It just doesn't make logical sense. Constant velocity is the change in position over the change in time. So if you have a constant velocity, that means your acceleration is equal to 0. So you cannot use equations 1 through 5 if you use the constant velocity equation. It makes no logical sense. None at all. So don't ever use the constant velocity equation unless you're having an acceleration is equal to 0.